In this episode, I will explain about the JK flip-flop, how you can implement the truth table, characteristics truth table, and also the excitation table. Hello guys, welcome to another episode at IB Electronics World, and today we are going to discuss about JK flip-flop. But what actually is the JK flip-flop? Is basically a gated SR flip-flop with as like this is an SR flip-flop with the addition of a clock input circuitry that prevents the illegal or invalid output condition that can occur when both inputs S and R are equal to logic level 1. Further, so practically you can create the JK flip-flop by using NAND gates. You can have two NAND gates with 3 inputs and a clock which is connected to both inputs of the NAND gates, and then are connected also to the another 2 NAND gates. And in addition, you can implement it by using AND gates, 2 AND gates and 2 NOR gates. And of course, you can use the microchip, which is already implemented in its JK flip-flop. But let's see now the truth table for the JK flip-flop. So you have 2 inputs and you have 1 output, which is the QN plus 1. Classic is you need to complete the truth table 0, 1, 1, and then 0, 1, 0, 1. So we know that in 0 and 0 there's no change, so we have the state of memory. So you have Qn, and then in 0, 1, when J is 0 and K is 1, you have 0, which is the reset, and 1 and 0, it gives you 1, which is set. And if you have both 1 and 1, this means Q and not, which means toggle the output. Let's see also the characteristic truth table. C8 truth table. So again, now instead of having only 2 inputs, we are going to have 3, which is going to be the previous stage, this stage here, and the next stage. So we are going to find out the next stage of JK, and the output will be again Qn plus 1. So because we have 3 variables, now it should be 8, so 4 zeros and 4 ones, and then 0, 0, 1, 1, easy, 0, 0, and 1, 1, and then 0, 1, 0, 1, 0, 1, 0, 1. So in order to find the output here, what's happening is you're going to look back. So the Qn JK, when the JK is equal to 0, 0, so this means you have the memory, so this means no change, as I said, and so you will have the output will be equal to the input Qn, so it will be 0. And when you have 0, 1 JK, this means it's reset and gives you 0, so you have 0. And then when it's 1, 0, you have set, which gives you 1. And then you have 1, 1, which is going to be toggle, but in that case the Qn is 0, so this means it will be the complement, so it will be 1 here. Again, you have 0, 0, and the Qn is 1, so the previous value, because we say that it not change, so it will remain 1. And then you have 0, 1, which gives you 0, but the Qn is 1, and it means it will give you 0. And then 1, 0, it gives you 1, so the output will be 1. And then 1, 1, and you have toggle, and the Qn is 1, so this means it will be 0. I think straightforward so far. And also, let's try to find out the excitation table of the JK. So the excitation table. So it's Qn and Qn. Again, you have two inputs plus 1. And then you have JK. Easy to complete the truth table, 0, 1, 1 and 0, 1, 0, 1. So this means when you have you have 0 and 0. So in that case here you will have 0, 0 and 0, 0. So this means the J is the same in both cases, so 0, and the K is 0, 1, which means we don't care. So we set X. Let's try to draw a line here. And then we continue to the 0, 1, which is this one here. And we see the J is equal to 1 in both cases. So we have 1, 1 and 0, 1 in K. So again, we don't care about the K. And then we have 1, 0, which is this one here, and 0, and this one. In that case, we have 0, 1 and 1, 1. So this means we don't care about J, and we set 1. And 1, 1 is the last stage, which is this one and this one. And we have 0, 1 and 0, 0. So this means X, we don't care, and 0. But let's go back also to the simulator and see. So actually I have the microchip 74HC76. Unfortunately, I don't have it physically with me, but I have it on the simulation. So let's run the simulation. As you can see here, I have connected a logic probe, so which is called logic state, and it gives you 1 and 1 and also 0. So in that case, I have also a clock which is 1 Hertz, and as you can see, it's blinking every certain time. And I have connected also a set and reset, which doesn't make a big difference, but we'll go through that in order to explain. So in both cases, do you remember here on the truth table, when we have 1 and 1, it should toggle, which it does. So you can see here it does. And one time it's the Q on, and after that, when it's positive edge, you are going to change to the second LED. If I will change one of these two inputs, J or K, we'll see, for example, if I will change the J equal to 0, we should expect the 0, which means the Q naught, it will be on. And if I will do the other way around, the K is, so practically the K is 0 and the J is 1, so in that case it gives you 1, which means Q is high, and you can see the LED of Q is high. And again, if both are 0, we don't have any change, we have the memory, so it's going to remain regardless of how many cycles of the clock we are going to pass. However, if you have both 1, and let's say that you're going to set the set to 0, you will see that automatically will stack to the Q, and the other way around for R, it will stack into the Q naught. And if both, you will see both, it will be on. So that was it for today. I hope you enjoyed this video. If yes, please share and subscribe, and I will see you in the next episode.